Welcome, everyone. Today, we're doing a deep dive into what's arguably one of the biggest hurdles for large language models right now, factual hallucinations. You interact with something powerful like GPT-4, and you often get amazing results, but there's always this risk, this tendency for them to generate answers that sound plausible, but are just, well, factually wrong or completely unsupported. And this isn't trivial, it's a genuine safety concern. Think about sensitive fields like medicine or finance. A single incorrect word, maybe a wrong date or figure, can completely change the meaning and lead to, frankly, dangerous outcomes.
Absolutely. And tackling this means we need really robust ways to detect these hallucinations. The problem is a lot of the tools and benchmarks we've had so far are quite limited. Most operate only in English, for starters. And they usually only tell you if the entire response seems off, that sequence level detection. But the real challenge, the thing we need for actual correction, is span level detection. We need to be able to pinpoint the exact words or phrases that are factually incorrect.
Right, finding the needle in the haystack, not just flagging the whole stack.
Precisely.
And this need for precise, multilingual, span-level detection is where our main source for today comes in, PsiloQA. It's a new dataset designed specifically to address these gaps. It covers 14 languages and focuses entirely on that fine-grained, span-level identification. So let's unpack how they built this thing and what it tells us.
Okay, maybe first it's helpful to quickly lay out the different ways researchers typically look at hallucination detection. There are sort of three main tasks. You've got sequence level, which we mentioned. That's the broadest, just identifying if an entire chunk of generated text contains any factual inconsistency. Then there's entity level. This gets a bit more specific. It tries to flag individual things like a person's name, a place, a date that seem wrong compared to the source material.
But even that feels a bit blunt, doesn't it? If you flag Paris is wrong in a sentence, you still don't know what about Paris is wrong.
That's the issue. It's better, but still not precise enough for automated correction or clear user feedback. Which brings us to span-level detection. This is the most granular approach. It's about identifying the exact segment of text, sometimes just one or two words, that is misaligned with the facts. It defines the precise boundaries of the error.
And getting that level of detail, especially across many languages, was the major bottleneck before PsiloQA, right? It sounds incredibly labor-intensive.
It really was. Creating high-quality, span-level data sets usually meant relying on human experts, domain specialists, carefully reading and annotating text. That's incredibly slow and expensive. Some datasets like RID Truth QA did achieve this for English, but scaling it multilingually was almost impossible that way. People tried shortcuts like synthetically inserting errors, but that doesn't really capture how LLMs naturally hallucinate.
So PsiloQA represents a different approach. They automated the whole pipeline to make it scalable and affordable, specifically aiming to capture real LLM errors. Let's walk through their four-stage process. Step one was QA pairs generation. How did that work?
They used GPT-4o for this. They fed it random passages from Wikipedia articles across the 14 languages they were targeting. Then they prompted GPT-4o to generate questions based on each passage, along with the correct golden answer drawn directly from that text. They also made sure to vary the difficulty, easy, medium, hard questions to get a good mix.
Okay, so they have context, question, and the right answer, all generated by GPT-4o. Then came step two. Hypothesis generation. This seems key for getting realistic errors.
Yes, this is quite clever. They took the questions generated in step one, but then they asked a range of other LLMs to answer those questions, crucially, without giving them the original Wikipedia passage, a zero context setting.
So you force the models to rely purely on their internal knowledge, their training data memory.
Exactly. You're deliberately putting them in a situation where they're likely to hallucinate if they don't actually know the answer reliably. This way, you're eliciting genuine, natural-sounding errors, not just swapped words or typos.
Okay, so now they have the ground truth passage, the question, the correct answer, and a potentially hallucinated answer from another LLM. Step three is the inconsistency detection, the annotation part.
Right, and again, they turned to GPT-4o. They gave it the original passage, the question, the golden answer, and the possibly flawed LLM hypothesis. GPT-4o's task was to compare the hypothesis against the ground truth passage and automatically insert HAL tags around the exact words or phrases in the hypothesis that were inconsistent. So if the hypothesis said 1989, but the passage said 1987, only 1989 would get tagged.
That level of automation is impressive, but also sounds like it could go wrong. Did they have issues with GPT-4o making mistakes or being inconsistent itself?
That's a valid concern, and why step 4 dataset filtration was so important. They didn't just take the raw output. They applied several layers of automated filtering, some based on rules, some using more prompts to clean the dataset. They removed things like subjective questions where there wasn't a clear factual answer, incomplete questions, or instances where the LLM just refused to answer properly. Quality control was built in.
So after all that, what did the final PsiloQA dataset look like in terms of scale and content?
It ended up being quite substantial. The final training set has just under 64,000 samples, 63,792 to be exact. It covers 14 languages. English has the largest share, about 23,000 samples, but having the other 13 provides that crucial multilingual breadth.
And the nature of the hallucinations, were they mostly single words or longer phrases?
Mostly quite short, actually. They found that over 50,000 of the hallucinated spans were fewer than 5 words long. This really underscores why that fine-grained span-level detection is necessary. The errors can be subtle.
What about the topics covered?
Pretty diverse, drawing from Wikipedia. The most common domains were geography and sports, each making up around 25–30% of the data, but there was a widespread beyond that.
Okay, the scale and multilingual aspect are clear wins. But the big question is always quality, especially with automated annotation. How did they check if GPT-4o was actually doing a good job with those HAL tags?
They did a manual verification study focusing on 100 English samples. They had humans perform the same span-level annotation task. Then they compared the human labels to GPT-4's automated labels. The results were strong. They found an 84.3% average precision and a 71.0% intersection over union score between the human and GPT-4 annotations.
So a 71% IOU means GPT-4o is identifying the error spans with pretty decent boundary accuracy compared to humans.
Yes, it indicates that GPT-4o, when provided with the ground truth context, can be a reliable annotator for this specific task, certainly reliable enough to create a large-scale dataset.
And this validation is crucial because it underpins the most striking claim, the cost effectiveness. Tell us about that comparison.
It's really quite dramatic. They estimated the total cost of using the GPT-4o API for all the labeling across those nearly 64,000 samples across 14 languages. The total was about $535.
$535 for the whole data set annotation.
To the whole thing. Now compare that to a rough estimate for the human-annotated RA-Truth-QA dataset, which is English only and span level. That cost was estimated around $3,000.
Wow. So PsiloQA's method is something like 17 times cheaper. And it delivered data for 14 languages, not just one.
That's the takeaway. It dramatically lowers the barrier to entry for creating these essential, high-quality multilingual resources. It makes this kind of research much more accessible.
Okay, so they built this impressive, cost-effective data set. The next step was obviously to see how well existing detection methods performed on it. They looked at 3 main types, right? Uncertainty quantification, encoders, and LLMs themselves.
That's right. They started with uncertainty quantification, or UQ methods. These basically look at the model's confidence scores. Methods like Focus, MaxProb, and CCP were tested. Focus generally came out on top among the UQ methods in terms of average precision, meaning it was fairly good at flagging that a response contained an error somewhere.
But the precision of where the error was located remained an issue. That IOU score again.
Exactly. The intersection over union scores for all the UQ methods were consistently quite low. It suggests that while they can sense uncertainty or inconsistency broadly, they really struggle to pinpoint the exact boundaries of the factual error. You might get a flag over a whole sentence when only one word is wrong.
Which isn't very actionable for correction.
Mm-hmm.
So how did the more traditional fine-tuned encoder models fare?
Much, much better, especially on precision. When they fine-tuned various encoder models on the PsiloQA data, these models significantly outperformed the UQ baselines. The standout was Membert, a modern multilingual encoder. It achieved the best overall performance looking at both IOU and average precision in 12 out of the 14 languages tested.
So having that multilingual pre-training really paid off for detecting errors across different languages.
It seems so. It highlights the value of models trained specifically on diverse linguistic data for this kind of fine-grained cross-lingual task.
And what about using other LLMs for detection? They tested FactScore, for instance.
Yes, FactScore is an LLM-based approach. Similar to the UQ methods, it showed decent average precision in some languages, suggesting it could identify the presence of inconsistency. But again, its IOU scores were consistently poor. It struggled with precise boundary detection, just like the UQ methods. It seems getting models to accurately self-critique at the word level is still a major challenge.
One of the really interesting findings, I thought, was about cross-lingual transfer. How well did training on the full multilingual PsiloQA dataset help performance on individual languages, especially low-resource ones?
This was a key result, shown in their Table 3. They compared models trained only on a single language's data from PsiloQA versus a model trained on the entire multilingual PsiloQA dataset. The results were clear. Training on the full multilingual dataset consistently led to better performance when testing on individual languages, even across very different language families and scripts. Think transferring knowledge from English or German to improve detection in, say, Arabic or Hindi.
So exposure to diverse languages during training helps the model build more generalizable detection capabilities.
It strongly suggests that, yes, high-quality, broad, multilingual data seems crucial for building detectors that can work effectively across the globe, not just in English.
They also tested knowledge transfer to other datasets, right? To see if training on the synthetic PsiloQA data generalized well to benchmarks annotated differently.
Yes, that was Table 4. They took models trained on their synthetic PsiloQA English data, PsiloQN, and compared them to models trained on the human-annotated QA dataset. They then evaluated both on independent external benchmarks like Mushroom, which also has span-level annotations.
And the PsiloQA trained models did well.
Remarkably well. The models trained on the synthetic PsiloQA data consistently outperformed the models trained on the human-annotated QA data when tested on Mushroom. They saw about a 45% improvement in IOU score on Mushroom.
A 45% jump in precision on an independent benchmark is huge. It really validates the quality and utility of their synthetic data generation pipeline.
It does. It suggests that the scalable, cost-effective synthetic approach can produce data that's not only useful on its own terms, but actually leads to more robust and precise detectors compared to smaller, potentially more expensive human-annotated datasets, at least in this comparison. So to wrap up the main findings, PsiloQA demonstrates a viable path towards creating large-scale multilingual span-level hallucination data affordably. And the evaluations on this data show that while UQ and LLM-based methods struggle with precision, fine-tuned multilingual encoder models like Member are currently the most promising approach for accurately identifying the specific location of factual errors.
It's only a significant step forward. But, as the researchers themselves point out, the entire PsiloQA pipeline hinges on one model. GPT-4o, both for generating the initial QA pairs and for doing the final annotation. This reliance introduces a potential single model bias. The types of hallucinations generated might be characteristic of GPT-4o's failure modes, and the annotations reflected specific judgment. So thinking ahead, what strikes you about the potential value, or maybe the necessity, of using an ensemble of different powerful models, maybe GPT-4, Claude 3, Gemini, etc., working together for the annotation step? Could that help create an even more robust and less biased dataset in the future?